Hi everybody. This is our lecture on section 4.4, which is on tangent planes. So with a single variable function, y equals f of x, okay, the slope of the line tangent to the curve at the point x equal to a, y equal to f of a, right, at x equal to a, y equal to f of a, is, well, it's the derivative, f prime at a, right? So I'll remember this picture from Calc 1, this sort of idea here. So here's the point A, x equal to a, y equal to f of a, and the slope of this tangent line, the tangent line is right there, and the slope is f prime of a. Now, with the two-variable function, with a two-variable function, z equal to fxy, okay, we have a plane tangent to the surface z equals f of xy at x equal to a, y equal to b, and then z equal to fx or fab. And the picture of it, we drew it last time, looks like this. So z-axis, y-axis, x-axis, and you've got this surface here. So let's say it's kind of bowing outward here, perhaps. All right, this is your surface. Saying bowing downward there, something like that. This is your surface z equal to f. Whoops. Z equal to f of x, y. And a given point on this surface, right here, the coordinates of that point are x equal to a, y equal to b, z equal to f, a, b. So that's that point right there. And then, remember, we have two different derivatives. We've got the derivative in the x direction, that doesn't look quite right. Let me try drawing this a little differently. Yeah, this will work better. All right, so at a given point on the surface, A, B, f of A, B, you have two tangent lines. you've got the line tangent to the surface in the direction of the x-axis. Line tangent to the surface in the direction of the x-axis, right, whose slope the slope of this line is equal to the partial derivative with respect to x of the function f at the point AB. And then you also have the slope of the surface in the y direction, so parallel to the y-axis, like that. And the slope of this one is the partial derivative f with respect to z at the point A, B. So, again, this is the surface, z equal f x y. This is the point here, a, b, f of a, b. And you have these two lines that are both tangent to the surface, one in the x-axis direction, the other in the y-axis direction, and then those two lines uniquely define a plane. And here it is. So this plane is the tangent plane to the surface at a, f of a, or a, b, f, a, b. So you can imagine we've got this line, and then we've got this line, and you can imagine that plane sort of as a continuum of lines parallel to that one. To the orange one and to the blue one. Okay, so you have tangency in two different directions. So tangency to the surface is not given by a line, but by a plane. Okay, something greater than that. Now, what's the equation of this plane? What is the equation of this plane? Well, if y is held constant, right, at y equal to b, okay, then the slope of the line in the x direction well, then the equation of the line in the x direction is, well, it's going to be z minus z0 equal to, well, the slope is the partial derivative with respect to x minus b. Actually, z0 will put f of a, b. Right, so in two dimensions, that's how you get the equation of the tangent line. it's y minus y of a equals f prime times x minus a. X minus a. Right, but here we're adapting it to the third variable, z. If x is held constant, at x equal to a, then the equation of the line in the y direction is, well, same as this. Z minus FAB equals the derivative. This time it's the partial derivative with respect to y minus b. Right? Therefore, the equation of the plane tangent to the surface at the point AB, FAB is, well, you just combine those two equations. So fxab, a minus b, plus partial derivative with respect to y at ab, y minus b. Right? Because in this equation, x is held constant to be, x equal to a. X is held constant to be x equal to a, so this becomes 0. And then you get that equation. And in the other equation, y is held constant to be y equal to b, which makes this 0. So you get that equation. So if x and y are both varying, then the equation of the plane, which always has this kind of form, looks like this. Okay, so that's the equation of the plane tangent to the surface at a given point. So that's with the partial derivative notation, or if you like the differential notation, it's partial f partial x at ab, x minus a, plus partial f partial y at ab, y minus b. So if you like the differential notation, or if you like the just sort of subscript notation, two different ways of looking at that equation. Okay, so let's just take a quick example of that. So here's a function, fxy equal to 20 minus x squared minus 7y squared. Find the equation of the plane of the tangent plane at x, y, z equal to, so we'll say x equal to 1, or no, x equal to 2, y equal to 1, right? So if x is equal to 2, that's 4. Y is equal to 1, that makes that 7. So it's 20 minus 11. 20 minus 11 is 9, square root is 3. All right, first of all, we got to find the partial derivatives. All right, the partial derivative of f with respect to x, and then you can kind of skip the x and y's, just keep the notation more free and not clutter it up. So the partial derivative of f with respect to x, right? This is 1/2 20 minus x squared minus 7y squared to the negative 1/2 times the derivative of the inside with respect to x. Everything else is constant. So 20 is constant, 7y squared is constant. This is just minus 2x. So it's equal to minus x over 20 minus x squared minus 7y squared. partial derivative with respect to y, 1/2 20 minus x squared minus 7y squared to the negative 1/2. Derivative of the inside, where 20 is constant, x squared is constant. So we just get minus 14y. The 14 cancels with the half, leaves 7. So we got minus 7y over this. 20 minus x squared minus 7y squared. So there's the partial derivatives with respect to x and y. So now the partial derivative at the points in question, right? So the partial derivative of f with respect to x at 2, 1 is equal to, well, x is 2, so it's minus 2 on the top. And then this expression was 3, minus 2/3. And then the partial derivative with respect to y at 2, 1. Well, the minus 7y is minus 7, and then this number down here was 3. So there's the two coefficients that go into the tangent plane equation. So here it is z, let's write it down, z minus f of 2, 1 equals partial x at 2, 1 times x minus 2 plus partial y at 2, 1 times y minus 1. So there's the equation of the tangent plane. Plugging in the numbers that we know, right? This is, copy that over, z minus 3 is equal to, so fx was minus 2/3, x minus 2, plus fy minus 7/3, y minus 1. So there's the equation of the tangent plane. If you want, you can expand it further, multiply this through, multiply the negative 2/3 through, the negative 7/3 through, but there's no need to do that. Okay. So now that we've got that example out of the way, and we've got this equation understood and how to use it for just a general function, what else, remember, what else does the equation of the plane hide within it? The equation of the plane hides within it the normal vector to the plane, right? Remember, normal vector and line to the surface. So with a plane, right, you've got that normal vector, this normal vector in A, B, C like that, gives you this equation right here, ax plus by plus cz equals d, whatever that d might be. Okay, so that normal vector is just, hiding in plain sight in the equation here. So once you get these partial derivatives and get the tangent plane, is established, that's z minus fab equals fx at ab, x minus a plus fy at ab, y minus b. The normal vector is what? Well, that's the equations of x, y, and z. When they're all on the same side of the equation. Here the z's on the other side. Right, so the coefficient of the z isn't 1. The coefficient of the z is negative 1 because I gotta move it over here. Right, the coefficient of x is fx, the coefficient of y is fy, and the coefficient of z, after you move it over here, is negative 1 because they all have to be on the same side of the equation. right? If this is normal vector ABC, then the coefficients on the same side are ABC. So here the normal vector is n equal to fx, and I'll leave out the AB, fy, -1. So the equation normal vector of the normal line to the plane at A, B, F, A, B is, so here we have to use parametric equations, right? X, Y, Z, you need a point on the line, which is this, A, B, F, A, B, plus the slope times t. So Fx times t plus Fy times t plus, or just minus t. Right? This is the slope vector for the line. That's the line perpendicular to the surface. So, for example, so for the surface given by fxy equal to 20 minus x squared minus 7y squared, at the point, the equation of the tangent plane at 2, 1, 3 is, so that's the one we found before. Oops. Where was it? Right there.
Hey, Dad.
Hi, baby.
Where's Mama? Where's Mama?
So this is the equation of the tangent plane. So the normal vector to the plane is minus 2/3 minus 7/3 minus 1. Right? It's a positive 1 coefficient here, but when we move the z over there, it's -1. Right? Or, I like positive numbers, 2/3, 7/3, 1. Just flip the vector around, but it's still normal. So the equation of the normal line to the plane at, what was the point, 2, 1, 3, is x, y, z, 2, 1, 3, plus 2/3 t, plus 7/3 t, plus t. So you've got the line tangent to the plane and the line normal to the plane. Or, sorry, you have the plane tangent to the surface and the line normal to the surface. Normal meaning is sort of another word for perpendicular. So we have this notion of a perpendicular vector to a surface at a given point now. All right. So another topic closely related to this is the notion of the differential. Given that function z equal to f a b and a point a, or z equal to fxy, and the point a b f a b, the equation of the tangent plane is z minus fab is equal to, let's use the differential notation, dz dx times x minus a plus dz dy times y minus b. This is often written as the change in z. The change in z. So this is z. This is some fixed z value, f of a b, and then this is some other z value. So this is the change in z between those two, is equal to dz dx times, this is delta x, the change of x relative to a. And this is dz dy times the change of y relative to b. Okay, so as with tangent lines, small changes in xy from AB correspond to a small change in z for z equal to f of x, and that change can be approximated with this differential expression. Be approximated by this. Come on. So, for example, right, so take z equal to this same function, right, and z of 2, 1 equal to 3. Okay, we can approximate z of 1.95 comma 1.08 by using the differential with delta x equal to, so 2 is the starting value for delta x. So here we got 1.95 minus 2. So that's negative 0.05. And delta y, right, the fixed y value for the tangent plane is 1. And here we're talking about y value 1.08. So the delta y is positive 0.08. So now delta z is equal to minus 2/3 delta x minus 7/3 delta y, which is equal to minus 2/3 minus 0.05 minus 7/3 times positive 0.08, which is approximately equal to minus 0.153333. Right? So z at that point, 1.95, 1.08, is approximately equal to, not exactly equal to, 3 plus delta z. Right, the delta z given by the differential. The tangent plane approximates the function for tiny changes of x and y. right? So this is equal to 3, right? That's the fixed value for z at the point 2, 1, plus the delta z. So minus 0.15333. And this is equal to 2.84666. Using a calculator, right, z of 1.95 comma 1.08 is equal to, well, the square root of 20 minus 1.95 squared minus 7 times 1.08 squared. So we can go to Wolfram alpha, or do it right here. 1.9 or 20 95, oops, 1.95 squared minus 7 times 1.08 squared, that whole thing to the 0.5. So 2.83420 2.83420 ... which is a very small difference, right? Less than 1/100th difference, which is an error of less than 10 to the minus 2. Right, so we see that tangent plane approximating the function for small changes in x and y. Large changes in x and y, of course, you're not going to get a good approximation, right? This was talked about a lot in Calc 1, right? This tangent line, it approximates the function for small variations around a. When you get large variations around a, there's a huge difference between the two, right? For large variations of a. But for tiny, tiny variations of around a, of x around a, the difference is small. Same thing with the tangent plane. All right? The closer you are to that point of tangency, the smaller the difference between the function and the tangent plane. So this approximation using the differential or using the tangent plane gets better and better the closer you get to that point of tangency. Okay, so that's the material for this section.